So, Ange, what is friction? This is our current most agreed to understanding of what friction is, although there's various models. We think it's due to the interlocking of molecular hills and valleys between a surface and an object on the surface. Even if you look at your desks, for example, although they look smooth, if you zoom in on the molecular level, we think that they are bumpy and jagged, and as you slide those objects across each other, those little jagged ridges catch onto each other and prevent or impede sliding. So on the atomic scale, nothing's really smooth. The key concept with friction is that it resists sliding. In fact, those are the two words that you want to underline, because that's how you're going to figure out the direction of friction. Because friction resists sliding, it can resist motion, like when you tried to slide your hand across your desk just now, but it can also create motion, like for walking or rolling for cars. Example 1 says, draw the direction of friction in each case. I apologize. It looks like there's a tiny gap between this box and the surface, like it's floating on a cushion of air. It's not. I just couldn't get it to quite get there. So pretend it's right on there. Okay? It wants me to draw the direction of friction on a sliding block. Jan, which direction is this block sliding? To the? Which way would friction be pointing then, folks? To the left, because friction resists sliding. So if I was doing a free body diagram, among other forces, I would have friction there. For some reason, by the way, I label the force of friction as a capital F and then a lowercase f R. I don't know why I put the R there. No textbooks do that. They all just do that. They put an FF, and you can. For some reason, I developed the habit of putting the force of friction there, and it's about the only time you'll ever see me write an unnecessary extra letter. I don't know why I do it, but I just do. So that's my abbrev for friction. Capital F, force, and then subscript friction. Which way is friction pointing for a car speeding up? Well, if we zoom in on the tire right there, it seems to me that the tire is pushing backwards against the road. Forces come in. The tire is trying to slide backwards. Friction resists sliding. So which way will friction be pointing? Yeah, this is really tricky for both students and grown-ups and even physics teachers to wrap their brain around. In this free body diagram, Eric, friction would be pointing forwards. I had a teacher years ago, they drew the free body diagram on a car. By the way, here's a car accelerating. What are the forces acting on this car? Get the obvious one. What else? What else? What makes a car go forwards? That's the free body diagram of a car that's accelerating. The diagram that they had drawn and they were teaching their students was this. They had gravity, normal force. They said, oh, friction always slows things down. And then they had engine, and they made engine bigger because the car was going forward, that's totally wrong. First of all, the engine does not make a car go forwards. Otherwise, cars could drive on ice, right? Does the car still have its engine? Yes, it does. What's missing on ice? Everybody? Friction. So I had to have a chat with that teacher, and that's not good. And to their credit, they realized, and they didn't teach. I've had some teachers, I'm just going to keep teaching it that way. No, got to teach it right. Hey, what about for a car slowing down? Well, now what happens, actually, when you apply the brakes, what you're actually doing is you're trying to get the tires to spin backwards against the pavement. In other words, you're trying to get the tires to slide forwards. Friction resists sliding. So when you hit the brakes, which way does friction point? The opposite of forwards. Everybody? And again, that's why you can't drive on ice. If your brakes was all you needed to come to a stop, You could drive on ice because you still got your brakes. What force is missing? Friction. What does friction depend on? Okay. First of all, we have to explain ice and we have to explain sandpaper. One of those has more friction. Which one? Ice or sandpaper? Sandpaper. Okay, so I guess let's call it stickiness or slipperiness. Friction depends on how sticky or slippery two surfaces are relative to each other. You okay with that? We have a symbol for stickiness, and the symbol is the Greek letter mu. This is called the learn to spell, Mr. Dewick. Coefficient of friction. The Greek letter mu, where's my mu? Here's my mu. Looks like this. This is why I have a mu handy. Okay, it sort of looks like a lowercase letter U with a droopy tail. It's where our lowercase m comes from. You can kind of see it hidden in there. Have I mentioned we're running out of letters? Because we've already used mu for, I think, micro in our metric system. We don't have enough letters to go around. I'm sorry, we just don't. So this is the symbol for stickiness. I wrote here, it depends on the types of surfaces that are on contact and how slippery or sticky they are with each other. This is represented by the coefficient of friction, symbol, Greek letter mu. It's a dimensionless quantity. What does that mean? Has no units. It's not a force. It's just a ratio. It's a ranking. The bigger it is, the stickier. The closer to zero, the slipperier. Can't be negative. So if mu is big, lots of friction. If mu is small, slippery. Really, I should say if mu is big, sticky. If mu is small, slippery. Just to give you some examples, steel on ice has a mu of about 0.01, near zero, but not quite, because you will eventually come to a stop. Rubber on concrete has a mu of about 0.75. Pretty sticky. If you have a mu bigger than 1, that's glue, because you can hold your own mass and more than your own mass. You can stick to the ceiling, say. Is that all right? So friction's going to depend on stickiness. That's the first thing. Does that make sense? You okay with that? Should be something to explain ice, oil, and sandpaper. What else does it depend on? Well, what's easier to slide across the gym floor? One of those wooden benches or one of those wooden benches with 10 people on it? Just the bench. So what else should friction depend on? At first, you might say the mass, and that's not a bad guess, but I'm going to pause the video for a second here. So friction also depends on the force pushing the surfaces together. In basic problems, the force pushing together will be mg, but in more complicated problems, when we're lifting up or pushing down, a better descriptor will be the normal force. So this is our next equation, and it's on your formula sheet. Friction equals mu times the normal force. It's how sticky or slippery an object is times how hard the ground has to push up to keep it from sinking in. By the way, what if you lift the object off of the ground? If the object isn't touching the surface, if you're carrying it, what's the normal force? So how much friction when you carry something? Ta-da! Which may be Captain Obvious. Well, of course, you're not sliding it across the floor, but no normal force, no friction. Okay. Did I give you that on your green sheet? And correct me if I'm wrong, is that the last equation in this whole unit? In that row? Yeah, that's it. F equals what? Ma. Weight is mg, the force of gravity. No, now. And then friction is mu times the normal force. You might end up memorizing those three, and if you do, great. You don't have to. But hopefully you have memorized F equals what? And hopefully you've memorized winner minus loser equals MA. Let's do a question. I like example 2. I like example 2. I like example 2. Suppose we are pulling a 6.5 kilogram mass across a rough surface at a constant speed. How hard do we need to pull? Emma, what's this question asking me to find? How hard we need to pull. I think it's asking us to find a force. Because force is like a push or a pull. Okay. Does anybody see the 2-word trigger phrase I should underline? Constant speed. If we're at a constant speed, what's our acceleration exactly as a number? So the forces must be, I'm looking for where it begins letter B. I'll bet you, Emma, I can't find how hard we have to pull, but I'll bet you I can find another force the same size as that. You know what this is a good job for? You know what this is a good job for? What? Free body diagram. Although, Emma, did they give me a picture? I'm going to label the picture. You could do the mass as a dot off in the margin, but 99% of the time, if they give me an actual picture, I'll just label the picture. So, Emma, what are the forces acting on this? Get the obvious one. Good. Is this mass sinking into the ground like quicksand? Is it flying through the air like Superman? So which way must there be an arrow pointing? Bigger, smaller, or the same size as mg? Will there be some Mr. Dewick where it's not the same size? Yes. Patience, we'll get there. But for now, what else? Well, I guess we have an F pull. Which way? Yeah? Why can't this be all? Why would this be impossible based on this question? Could that be at a constant speed? Why? Because the forces are not. I'm looking for where that starts letter B. Emma, which way must I draw a force pointing to the? Bigger, smaller, or the same size as F pull? Okay. What force is that, boys and girls? How do I know? Because they said rough surface. In fact, they even gave me a coefficient of friction. And friction resists sliding. Since we're sliding to the right, friction's to the left. Normally, I would say who's winning, who's losing. But what 2 words do we underline? It's a tie. I think I can say this. What did they want me to find? F pull. Well, I can say F pull has to be the same size as friction. So I can't find F pull, but what I can find, Mud, is how big friction is, and knock, knock, who's there? That'll be the same size as F pull. What's our new equation? Friction is what times what? Emma? Mu. What's mu? I don't know. What's mu with you? Okay. Whatever dumb way you want to remember it, what does a Greek cow say? Mu. What does a Greek cat say? Mew. There's all sorts of dumb jokes, but mu times the what? Good. Ah, rats. I don't know the normal force. Oh, but look. I know the force that has to be the same size as the normal force. What? Okay, so I'm not saying friction is mu mg. I'm saying friction is mu times the normal force. But in this question, in a wonderful coincidence, even though I don't know the normal force, I know it has to be exactly the same size as mg. So I can say this. F pull equals mu mg. Emma, what's mu? I don't know. What's mu with you? What's mu? 0.65, 0.64. Sorry, I misread that. M. Yep. G. Yep. By the way, in this specific question, constant speed, as far as I'm concerned then, I can give you any 3 of sorry, any two of F pull, mu, and M. Well, I guess any three of F pull, mu, M, and G, and you can find whichever one you want to. Yeah?
I don't get why we won't.
Are we sinking to the ground like quicksand? Are we flying you like Superman? Vertically, that means the forces must be, I'm looking for a word that starts with letter B.
No.
So that must mean that the normal force and mg are the same size. And so I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. mg. That was the chain of reasoning. We've had practice with doing that. So you'll catch up. What do you get? Sorry? Anyone say it loudly enough that I can hear? 40.8? Is that right? Units, it's a force, Emma. Newtons. Before you turn the page, I'm going to introduce a new term to you. This mystery force coming from off the page, we often call it the applied force. We say something is applying a force. I don't care what it is. It could be invisible leprechauns for all I care, invisible angels for all something is applying a force. And so I'm often going to refer to this as F applied, F-A-P-P. So F applied is mystery force coming from off the page that I don't want to make a big story about, but there's clearly a force there. Turn the page now. Note, we give a special name to an unknown force appearing from an outside source. We call it the applied force. Symbol F. Okay. Example 3, we're just going to continue building on pulling something across rough ground. Suppose we're pulling on that same 6.5 kilogram mass across the same rough surface. It's got a mu of 0.64 with an applied force of 86 newtons. Ooh. Dan, what does this want me to find? You know what this is a good job for? How do I know? First of all, it told us the applied force. Is there also friction in this question? Is there more than one force? That's a job for a free body diagram. Did it say the net force? Okay, so free body diagram. Dan, what are the forces acting? Oh, did they give me a picture? I'm going to label a picture. What are the forces acting on it? Get the obvious one. Good. Is it sinking to the ground like quicksand? Is it flying through like Superman? So there has to be a force pointing up the same size as gravity. And mud, that's what we have called the normal force. The normal force is a surface pushing back to prevent an object from sinking into it. And I always know how big it is. It's as big as it needs to be to prevent the object from sinking into it. What else? Okay, which way? Okay. What else? Psst, it's at the top of the page. See how I put that right there quite cleverly? It's right there. You just wrote it down. Look up one line. Oh, yeah. The something force starts with letter A and then a P. There we go. We'll call that F applied. Okay. Bigger, smaller, or the same size as friction. How do I know? What's this asking me to find? I think bigger. I think we're accelerating. Now, it's possible I might be wrong. It's possible friction could be larger and we're slowing down. If I got a negative acceleration, I'd know I'd guessed wrong and I'd have to quickly rejig the question. Meanwhile, Dan, what's this asking me to find? Who's winning? Vertically, it's a tie, so we're writing a horizontal force equation. You're right. What did you say? F applied. Who's the loser? Brea, did you... Wow. What? Bonson Park, you can take him. So bad. Fine. Who's the losing force, Dan? Yep. What does winner minus loser always equal? What are we trying to find? Get the A by itself. Ooh, Nick's theorem. Right? Okay. I know F applied. How big is F applied? 86 newtons. But I need to do some work with friction. So on my next line, I'm going to expand this a little bit. I'm going to say A equals F applied minus friction is what times what, Dan? This is our new equation for the day. It's on your green sheet if you're not sure. Mu times the normal force all over M. Dan, do I know F applied? 86. Do I know, hey, what's mu? I don't know what's mu with you. Do I know mu? What? You're right. It's in the question. Read. You'll see it. 0.64. Oh, mud? I don't know the normal force. Oh, but look. I know another force that has to be exactly the same size as the normal force. Which one? That's the little leap we're making here. So I think, Dan, I can rewrite this as F applied minus mu mg all over m. I'm showing every step in my notes right now. If read in the homework you get fairly good at this and you think I can go from this line to this line without the intermediate, I'm not going to panic or freak out, but this is just to let you know our thinking. I think now we can plug and chug. Dan, what was F applied? Good. Minus what's mu? I don't know. What's mu with you? M? G? Divided by? This is one all of you should practice typing in because this is kind of the level of difficulty. Actually, a little bit harder than this. We're eventually going to have more than one mass in these questions as well. But you should be able to type this in and get an answer. Dan, what'd you get? Okay. Sorry? I don't think so. Is this a fraction? Did you put the top in brackets? So you went like this. Your calculator. Bracket 86 minus 0.64 times 6.5 times 9.8. Close off the top. Divided by 6.5. Is this a fraction? Is there more than one thing on the top? Brackets around the top. Yeah, 6.9. Someone said 6.95. Why would I frown at them? It's definitely 6.96, yes? We round off, we don't chop off. Running out of room here. Let's go like this, Mr. Duick. A equals 6.96. Dan, units, its acceleration? Good. Okay. Example 4. Suppose we're pulling on a 6.5 kilogram. You know what? It's the same question, but I think all I've changed is the applied force. What might this be a good job for? I'm going to say try this one on your own. I'll do it quietly up here without saying anything. I won't freeze my screen, so if you get stuck, you can just look up. But see if you can find A. Free body diagram. I have a good calculator. I think I can just backspace and edit without having to retype the whole thing. And if you're done, just look up and kind of give me a nod and I'll know thumbs up. Yeah. By the way, if you all look up for a second, please. This first equation, winner minus loser equals m, let me put it back to the original. Far as I'm concerned, I could also give you A and say find F applied. How would you get the F applied by itself? Add the, yep, okay, fair game. As far as I'm concerned, I could give you A and F applied and say, find the force of friction. How would you get friction by itself? What's right in front of the friction that I don't like? The minus sign. I would sloppy dance. As far, and this is hint, hint, I like this question, I like this question, I like this question. As far as I'm concerned, I could give you A and F applied and ask you to find mu, the coefficient of friction, how sticky this object is. Which of those three expressions contains the mu hidden inside of it? Which of these three has the mu hidden inside of it? Friction. I would get friction by itself first, and then how would I get the mu by itself? How would I move the normal force over? What's the normal force doing to the mu? Multiplying? So we'll do one like that, but I'm telling you, as far as I'm concerned, Brent, all those are fair game. Okay? Let me restore the equation back to the way it was. Next page. Oh, we get to vote again. This is good, 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 good. A student gives an old shopping cart a big push across a flat, rough surface. What do I mean by rough? Include friction. Which of the following is the best free body diagram for the cart after the student has released it? Look up. I don't have a shopping cart, but I have an office chair with wheels. And this floor is a little bit rough. So what we're talking about is not while I'm pushing it, but after I let it go while it's still moving. So we're talking about right here, but not there. Which of those four is the best free body diagram? You know what? We're gonna vote. How high you hold your hand up is how sure you are of the answer. Boy, Mr. Duick. Okay. So we have, oh, and the motion is to the right. We're pushing it to the right. All right, let's vote. You ready? Oh, no, people are still thinking. I'll give you another 20 seconds or so. They're having a big argument in the back there. I like that. That's good. All right. Okay. Who says, Mr. Duick, it's got to be A. It's A. 1, 2, 3, 4, 5, 6, 7, 8, 9. Jan was a bandwagon 9. He looked around and then voted. Jeez. Who says, no, it's got to be B? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. C. No one. Really? Wow. It's got to be D, right? It's D. D. Convince me. Mud. What are you defending? Okay. You know what? Let's go process of elimination. If D was correct, how would the object be accelerating? Why would it be accelerating? Why would it be speeding up? We have an unbalanced force. Okay? So can we agree? No. How would this be moving? Ange? What would the acceleration of this be? Why? Because forces are, I'm looking for where it starts to be. So it would either, if it was stopped, stay stopped, or if it was pushed, it would just keep going forever and ever and ever and ever. Is that how shopping carts behave? No, no. Okay. Why must B be wrong? Because it is. Sorry, folks. How would this object move? Well, it depends. If this arrow to the right is a little bit longer than that, and it kind of looks like it is, then you might say it would have to be doing what? Speeding up. Yeah, accelerating. Or if you said those two arrows are the same size, that means the forces must be. Now, why do so many people pick B? Again, you're confusing force with velocity. Yes, it has a forward velocity, but there's no force pointing forwards after I let it go. What are the forces acting on it after I let it go? Get the obvious one. Get the obvious one. Right there. Is it sinking into the ground? No. And what else? Friction slowing it down. And that's how I know it will eventually slow down and come to a stop. Oh, and then once it stops, it'll stay stopped. Is that okay? It says explain your answer. What did I fall back on to explain my answer? Which one of Newton's laws? Okay, so the fact that Reed said third and sadly picked the wrong law, we can't just write the law, we're going to have to write it out. So we have to say something like this. Forces aren't balanced. We need an unbalanced force to the left to slow down. And that's the only A has that. Or you could have said Newton's first, dropped the mic and walked off, and I'd say, I gotcha. But, okay. And I know forces aren't balanced because it's slowing down. It's accelerating. And are we okay? I'm going to use the word acceleration even for slowing down. What I really mean is its velocity is changing. The forces are unbalanced. Sorry? Is that all right? Example 6, Gershine. What's example 6 asking me to find? Read very carefully. It's not asking me to find friction. What? Hey, what's mu? I don't know. What's mu with you? It's wanting me to find the stickiness. Fancy word. The coefficient of friction. Okay. Well, any guesses on what this might be a good job for? Free body diagram. So let's, oh, did they give me a picture? Well, then let's label the picture. What are the forces acting on this 5? Get the obvious one. Which way? Good. What else? Which way? Bigger, smaller, or the same size as mg? Okay. When won't it be the same size? We'll have questions that we get to where we have other vertical forces in the question. Someone's lifting up or someone's pushing down. We'll get there. But for now, same size. What else? Well, I see that 12. What have we decided to call the mystery force coming from off the page, Dan? Yes, good. So I'm going to, you know what? Since they already put an F there, I'm going to put an arrow just so that I can remind myself I noticed it. And I'll put a little up underneath the F. F applied is 12. What else? Bigger, smaller, or the same size as F applied? I think smaller. Now, when would it be bigger? If the question said slowing down and comes to a stop. Well, then I would know friction was winning. Right? I'm going to assume smaller. What's my equation? Yep. Equals. Yes. Okay, and I said to you, as far as I'm concerned, getting any one of these by itself is fair game. Oh, but actually, what's this wanting me to find? Mu. Where is mu hidden inside of which of these? So I'm going to get friction by itself first. That's step one. What's right in front of the friction that I don't like? Swappy dance. I'm going to plus this to there. I'm going to minus this to there. And I'll get F applied dropping down like a domino minus MA. That equals friction. If in your homework you want to combine a few of these steps and you're getting the right answer, you can. But on a test, I would show every step, and in my notes, I'll show every step. What am I trying to find, Grishit? Where is it hidden inside of? Oh, friction is what times what? Our new equation for today. So my next step, I think, would be to say F applied minus MA equals mu times the normal force. And now I can get the mu by itself. How would I get the mu by itself, Grishit? Divide what? In fact, this sort of looks like Nick's rule, but not with an A, with a normal force. But it's the same idea. Oh, problem, Mud. I don't know the normal force. Oh, but look. I know another force that has to be the same size as the normal force. Which one? Because we're not sinking into the ground like quicksand, and we're not flying here like Superman. You're starting to see Newton's first. Very helpful. So I think I can say this. Mu is going to be F applied minus MA all over mg. Mr. Dewick, do the m's cancel? No. If there was an m in all three terms, then yes. If the F applied had an m in front of it, then yes. But in this case, no. But we are at the plug and chug stage. I mean, complicated plug and chug, but plug and chug. So let's see if we can do this. What's mu? I don't know. What's mu with you? 12 minus 5.8. Starting to see why I said it's worth memorizing units, because I'm not even reading the question. I'm looking for numbers and units and just sticking them in wherever I need them. Divided by 5. Oh, I might be able to do that one in my head. It's going to be 12 take away 4, which is 8 over 5. Yeah, I can do that. 1.6? No.
I forgot that.
I forgot the 9.8, Mr. Dewick. Well, that was silly. So it's going to be closer to like 0.16, but I can't do that one in my head anymore because 9.8 is yucky to do math with when you're dividing. I got to type this in. Dan, is this a fraction? More than one thing on the top? Bracket. And brackets around the bottom as well. 0.163, blah, 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 blah. Okay. Grishit, what are the units? Do you remember? Your hint is, it's a trick question. No units for this. This is one of the few things you'll get. No units. By the way, really, it's newtons divided by newtons, which cancel. Who remembers, is that slippery or sticky?
Slippery.
That would be pretty slippery. That there, that's about rubber shoes on a mud puddle mud, the kind of mud or clay that you will slip on, not quite like ice, but you're like, okay, I'm walking on this and I really have to watch my balance. That would be about that. You would not be comfortable casually walking on a surface with that mu. You would have to be paying attention to your walking. You don't need to memorize that, but I always, whenever I show you a new concept, I like to try and give you an idea of what's big and what's small. Okay. Holy smokes, we are going to finish the lesson. Okay. Suppose we are pulling on an 8.5 kilogram mass across a rough surface with a force of 48 newtons. Okay. Ashley, what does A want me to find? You know what this might be a good job for? How do I know? They didn't say net force. There's definitely more than one force in this question. I better get organized. Did they give me a picture? I'm going to label the picture. What are the forces, Ashley? Get the obvious one. Yep. What else? By the way, now that we're deep into forces, I'm going to give you fewer and fewer hints. So you notice I'm not doing all the song and dance. I'm just saying, what else? So what else, Ashley? Bigger, smaller, the same size as mg. Okay. What else? Sure, I agree with that. Which way? Yep. What else? Which way? Okay. Who's winning? I think so. Who's losing? Equals. Okay, we're going to see if we can take some shortcuts. Let's see. I'm going to write out the original equation. I always write that one out. Ashley, get the A by itself. Okay, Callie's racing ahead. Callie, you're going to find something kind of weird, if you haven't already. A equals F applied minus friction, Ashley, is what times what? I don't know the normal force. Oh, but look. I know the force the same size as the normal force. Yep. Can I do that? Now, here's what you can do. Look up. If you want to, you can write mu Fn over m, and then you can say, oh, wait a minute. I don't know the normal force. It's the same as mg. If you write it and just cross out the Fn and put a little mg beside it or above it or something, I'll clue in that you've made that substitution, but you didn't feel like rewriting the whole thing just for that. You okay with that, Lena? I'm good with that. Does anybody plug in numbers? What's weird? Let's keep going. Okay. Fine. A is going to be, what was F applied? Ash? They told you. What? Yeah, they told you. Don't overcomplicate it. Minus, what's mu? I don't know what's mu. 0.64 times m times g all over m. What happens when you type that into your calculator? What was weird? Okay, you're going to get a negative acceleration. And what does that mean? It means we picked the wrong winner. The wrong winner. Friction is actually bigger than F applied. Okay? But it's an easy fix. First of all, hopefully you would notice, negative? I have to at least assume you'll catch that. So here's what it means, Ashley. Instead of winners pointing to the right, winners are going to be pointing to the... Okay? So everybody look up. This is how Mr. Dewick would fix it. Keep looking up. Okay, I want you to watch. I would go, And if you did that, I'd clue in. Yes? Okay. And then I'll do this in red. F applied, winner or loser? Put a minus in front of it. Friction, winner or loser? Put a plus sign in front of it. And if there was more forces, I would continue to walk through my equation and just ask, which ones do I need to adjust? Which ones don't I? And for really complicated situations, which we will get to, some you'll need to adjust, but some might have been right anyhow. Okay? And now it's a fairly, minus, plus, yes? Minus, plus, yes? Good, now what do you get? In this case, because I gave you a really easy version, I think you get the same magnitude of acceleration, but without the negative. Is that correct? That won't always be the case. In other words, you can't, Zach, simply say, I got a negative, I'm going to chuck the negative, and that's the right answer. Today, yes. But as soon as we have more than one mass in the equation, that might not be the case. And we're going to get to multi-mass questions. But my point is, Ashley, it's a pretty easy fix. It catches your eye, negative, and then it's make your winners losers, make your losers winners. In fact, if you're lucky, you might be able to just backspace on your calculator and insert some negative signs and replace some minuses with pluses, and you're good to go. Is that all right? So if you get a negative, don't just chuck it. If you get a negative acceleration, Nick, don't just, oh, must be positive and I'm right. Go back and check for simpler questions like this. Yeah, the answer you'll get would be the same magnitude. But for more complicated ones, you won't. When you hit equals on your calculator, you might get a different magnitude. Is that all right? What do you get? Point 0.6. Can you give it to me the 3 sig figs? 0.625? Is that rounded off properly?
Yeah.
Units, Ashley? It's an acceleration. Yes. Ooh, direction. Yes, slowing down. Okay. Is that right? Good. So what does this answer tell us about the motion of the object? What did we just say? It's got to be slowing down. Okay. Yeah.
Sorry, how is it slowing down?
What direction is the acceleration? That way. So we're pulling it this way, but it's accelerating that way. It must be slowing down. Eventually it'll come to a stop, but right now I think at this moment in time, because it says we are pulling it, let's assume we're moving. Yeah. What's your homework? Number 1? Two is good. 3 is good. 4 is good. So far I've assigned them all. I know 5 is good. 6 is good. I'm going to put a star next to 6, so easy that it's tough. 7 is good. I'm going to put a star next to 7. 8 is good. 9 is good. Okay, you know what? I assigned all of them, and I assigned a bunch of homework yesterday, and I want to show you cool videos, but I'm not going to show you them today. Tomorrow, we're going to mark the take-home quiz, but then I'm just going to press pause after we mark the take-home quiz. Make sure I don't forget to show you the videos, and we'll also just press pause. You can work on the homework from yesterday and today. Okay? It's also my way of saying you want to try and be caught up by, what day is tomorrow? By Thursday, ideally, you want to be, caught up with us, okay?